Before we look at the center of gravity of a system, let's consider the position of the line of action of the resultant force on a system. In this case, our system is a uniform bar. We can forget about its weight, so I'm not showing the weight vector here, which would be at the center of mass, or center of gravity. Okay, so we can imagine this bar is in outer space. It's being acted on by these three vertical forces. The bar itself is horizontal. We use the principle of moments to get the position of the line of action of the resultant force on this bar. So we can pick any point to take the sum of moments about. A convenient point is this point here, because the moment of the 4 Newton force will be 0. So that makes the calculation simpler. So the moment of the 3 Newton force about 0 is 3 times 1, 3 Newton meters in magnitude. It's a clockwise moment, as you can see, so it's going to be minus 3 Newton meters. And as for the 2 Newton force, its moment about 0 is 2 times 2, or 4 Newton meters. It's a positive moment. So our answer is 1 Newton meter, plus 1 Newton meter. Now the resultant force on the system is plus 3, plus 2, minus 4. That's 5 minus 4, which is 1 Newton. We get a positive answer, so the resultant force is pointing upwards, the positive direction. Now let's get the moment of the vector sum of the forces, or the moment of the resultant. So we have to multiply plus 1 by x, where x is the position vector of the line of action of the resultant force. And by the principle of moments, the moment of the sum equals the sum of the moments. So we can see that x equals plus 1 meters. So we know that the sign is important. So plus 1 means that the position vector is pointing to the right. Its tail is at the origin. Now, a very important point about the line of action of the resultant force is that the sum of the moments of the forces on a system about the line of action of the resultant force is 0. Now this is easy to prove, but let's just verify it in this example here. Then we will have a quick look at the proof. So we're going to get the sum of the moments of the forces about F, well, the line of action of F. Well, for the 3 Newton force, we have a clockwise moment about the line of action of F. So we multiply 3 by 2, we get 6, and it's minus 6. As for the 4 Newton force, it is an anti-clockwise moment about this point here. So it's going to be plus 4 by 1, plus 4. And finally, for the 2 Newton force, that has an anti-clockwise moment about this point. It's plus 2 by the perpendicular distance, which is actually 1, 2 minus 1, so we get plus 2. So you see we get minus 4 plus 4 plus, minus 6 plus 6, which is 0. So this fact is true for the forces on any system, and it's something that we will see in the case of the center of gravity of a system. The sum of the moments of all the forces on a system about the center of gravity is 0. So to prove this, we just note that by the principle of moments, the sum of the moments of the forces on the system about any point is equal to the moment of the sum or resultant of the forces about that point. So we can choose our point to be anywhere in the system. So what we do is we choose a point on the line of action of the force. So let's call this point A. So the sum of the moments of the forces about the point A is the moment of the sum of the forces about A. But we know what the answer is to the right hand side of this equation. The moment of the sum of the forces about A, where A is on the line of action of the resultant force, is 0. That's just the definition of the line of action, the position of the line of action of the resultant force. It's positioned in such a place that the moment of well, actually you can see that the distance of the point A to the line of action of the resultant force is 0. So the moment of the resultant force about the point A is 0, or about any point on the line of action of the force is 0. Now, the center of gravity, abbreviated COG, of a system is the unique point about which the sum of the moments of the gravitational forces or weights on the system is 0. Let's start with a simple system. This system consists of 2 particles, so we can ignore the dimensions of these particles. They are essentially point masses. This particle has mass 2m, twice the mass of this second particle. Now the particles are a distance of 1 meter apart, and they lie on a horizontal line. Now they could be in free fall. Of course, we know that all objects fall at the same rate, okay, if we ignore air resistance. So these particles will remain lying on a horizontal line as they fall towards the Earth's surface. So we imagine that these two particles are near the Earth's surface. So that means that we have constant forces acting on them. Now in reality these forces point towards the center of the Earth, but since the Earth is so big compared to the distance between these two particles, these forces are vertically downwards. And that will be the case in all the examples we do. In any system we do, the gravitational forces, or the weight of each part of the system, is vertically down. Now, it's possible too that these two forces could be resting on some horizontal surface. Okay, and we could still talk about the center of gravity of the system. If the particles are resting on a horizontal surface, then we have other forces, of course, acting on the particles. We have these contact forces. But we are not interested in the sum of the moments of the contact forces. We are only interested in the sum of the moments of the gravitational forces about a particular point. So where is the position of the center of gravity in this system? Well, let's get the line of action of the resultant gravitational force on this system. Well, it's clear that the resultant gravitational force is 3 mg newtons downwards. Now, intuitively, we expect the line of action of the resultant gravitational force to be closer to the 2m mass than to the 1m mass. So, let's get the sum of the moments of these two gravitational forces about this point. So this is easy to do, because the moment of the 2mg force about this point is 0, since this point lies on the line of action of this force. What about the moment of the 1mg force? Well, we multiply 1mg by 1, the perpendicular distance of the line of action of this force to this point is 1 meter. That's the way, because this is a horizontal line. So we just multiply 1 by mg, that gives us mg. This is a clockwise moment, so it's negative. So now we get the moment of the sum. So the resultant force is minus 3 mg. We take upwards as positive, the usual convention, and we have to multiply this by x, where x is the position vector of the line of action of the resultant force. By the principle of moments, these two are equal to each other. So solving, we get x equals plus 1/3. So we took moments about this point. This is the origin point, or the 0 point. So the position vector is plus 1/3. So we go 1/3 of the way along this line here, and that gives us the position vector for the line of action of the resultant force. So here's the line of action. Okay, so the center of gravity of the system lies somewhere on this line. Now, intuitively, we expect it to be here on the line joining the 2 points. Now, one way we could actually prove this is to imagine the system rotated. So we have the exact same system as before, same masses. One is 2m, the other is 1m, and the distance between them is 1m. So we haven't moved the particles in this system relative to each other. The particles are in the same relative positions as before. We just rotated the system. We've actually rotated it through 90 degrees. Now let's look at the forces on the system. Well, we have force 2mg acting downwards, of course, and we have a force 1mg acting on this mass. So we're looking at the forces, just the gravitational forces on the system. Again, the particles could be freely falling towards the Earth's surface with no air resistance, or both of them could be resting on horizontal surfaces, and we could still discuss the center of gravity of the system. Now, suppose we got the sum of the moments of the gravitational forces on the system about this point here. Well, the answer would be 0, because the perpendicular distance of this point to the line of action of both of these forces is 0. So it's very easy to calculate the sum of the moments. Now, what about the moment of the sum? Well, the moment of the sum must equal 0 as well. So that means that the line of action of the resultant force must be on the line joining the 2 particles, because the moment of the sum is, minus 3mg times x. So x is the position vector. So you can see that x has to be 0. okay, if we solve this equation. So the resultant force lies on this line and its magnitude is 3 mg. But the center of gravity lies on the line of action of the resultant force. So the center of gravity must lie on this line here. But it must also lie in this line here. So it lies on this vertical line and it lies on this horizontal line. So indeed it is here. It's on the line joining the particles, which is fairly intuitive. So here we are dealing with two particles in a plane. We looked at the system in two different orientations and we got the line of action of the resultant force for both orientations. The center of gravity must be on both lines, so the only way that can happen is if it's on the intersection of the two lines. Now, for some purposes, we can replace our system of two masses by this single mass, this single particle of mass 3m positioned at the center of gravity. So now our system is greatly simplified. We just have a single particle. Now let's consider a more complicated system. This time we have three particles, not lying on the same line, but at the corners of an equilateral triangle of side 1 meter. Now we can imagine the particles joined by very light rods, so light that we can ignore the masses of those rods, or indeed the system can just consist of three particle masses. These could be in free fall near the surface of the Earth, or they could be resting on horizontal surfaces. So anyway, the resultant gravitational force is minus 3 mg, okay, if we take upwards as positive. Okay, let's apply the principle of moments to get the line of action of the resultant force on these three particles. By the way, these three particles are in a vertical plane. It's not the case that, say, one of them is into the screen or out of the screen, okay? We've got to imagine that the three of them are in a vertical plane near the surface of the Earth. Now, A is a particularly convenient point for getting the sum of the moments about. A is the midpoint of this side of the triangle. It's a fact that if we draw a vertical line from this corner of the triangle down through this side here, it will bisect the side at right angles. So the moment of this particular force about the point A is 0, since A is on the line of action of this force. Okay, so we can forget about that. What about the moment of this force? Well, it's going to be positive because it's anti-clockwise about this point, so it's plus mg times a half, or half mg. Half is the distance from here to here, and for the other one it's minus a half mg. So we can see that, and of course for this one here it's 0. So the sum of the moments about the point A is 0. Okay, the moment of this force here about the point A is negative because it's got a clockwise moment about this point. It's mg times a half, or with the minus sign. Now the moment of the sum must equal the sum of the moments, which is 0 by the principle of moments, and that's given by, you know, the force minus 3 mg times the distance x. Well, x must be 0 obviously, so the line of action of the resultant force passes through this point here. So we can put our resultant force on this line. Its magnitude is 3 mg and it points vertically down. Now we know that the center of gravity of the system lies on the line of action of the resultant force. Intuitively we expect it to be somewhere in here, but how do we find the point exactly? Well, we can imagine rotating the system. So let's name this mass 1, this one 2, and this one 3. Of course these are identical masses, but if we rotate the system, you know, number 1 could end up over here, number 2 could end up here, number 3 could end up here. Now we haven't changed the system. The position of the particles relative to each other is still the same, and the masses are still the same. But in exactly the same way we could calculate the line of action of the resultant force, and we would find that it's this line here, and this is the line from mass number 2 to the midpoint of the opposite side. So the center of gravity must lie in both of these lines, so the only way that can happen is if it lies on the intersection of these two lines. Of course we could have taking another rotation of this triangle. So particle 1 ends up here, particle 2 ends up here, and particle 3 ends up here. Then the line of action of the resultant force would be on the line joining particle 1 to the midpoint of the opposite side. So the line of action would be this line here. And it's a fact that these three lines are concurrent at the same point. So here we could actually have a kind of a physical proof, if you like, of the fact that the three medians of a triangle are concurrent. That is, they pass through the same point. Of course, this is a simple triangle. It's an equilateral triangle, but this fact is true in general, actually. If we draw in any two medians of our triangle, so the triangle doesn't have to be equilateral, providing we have the same masses, identical masses at the corners, then the intersection of two of the medians is the center of gravity of the system. So a median is just a line got by connecting a corner of the triangle to the midpoint of the opposite side. So the center of gravity has the property that the sum of the moments of the forces on the three particles about this point is 0. If we actually attach the string to the top corner of the triangle so that the triangle is free to rotate about this point, okay, so we have a situation like that. Okay, so this is some string, and here's, say, a triangle consisting of three particles at the corners, nothing in between. Okay, the particles could be attached by very light. It's a very light rod, so light that we can ignore its mass, ignore its weight. Okay, the triangle would, balance in this position here. That's very clear. And if we just extend the string by drawing this line, we would have the line of action of the resultant force on the system. So we could draw in this line, then we could attach the string to a different corner of the triangle, and again we draw in this line here, and we have where the two lines intersect, we have the center of gravity. So that's true for three identical particles attached by very light rods, so light that we can ignore the masses of those rods. It's also true for a triangular lamina, as we'll see later on. A triangular lamina is a triangle, say, that's made out of cardboard, so the thickness is constant, the density is constant, so the mass is evenly distributed throughout the lamina. Okay, so you'll find that the center of gravity is found by getting the intersection of any two medians. So we join a corner to the midpoint of the opposite side. So that's true for a lamina as well, provided it's uniform thickness and the density is uniform. Well, a lamina, the thickness can be ignored, okay, so we can just treat it as a two-dimensional object, like we're dealing with particles here in a plane. The three particles are in a plane and their dimensions or thicknesses can be ignored. Now let's consider this system here. It's a uniform horizontal bar near the surface of the Earth. Now we can assume that this is just a one-dimensional object, so it doesn't have any thickness. So it's just a line, essentially. We could think of it actually as a line of particles. Okay, a line consists of points, as you know, and each of these points has a certain mass. So we have a line of point masses that all have the same mass. We can consider the weight of each of these particles. Well, this is a tiny mass, okay? So we use the letter D to represent that, dm, for an infinitesimal amount of mass. So the weight of it is the mass times g, dm times g, and if we sum up all those weight vectors for the entire bar, okay, I won't do it, we will get the total mass of the bar, okay, which we can call mg. So mg is some vector that will point downwards, of course. m is the total mass of the bar. So if we get the vector sum of all these vectors, that's easy to do because they're all pointing in the same direction. We will get one big vector pointing downwards, and its magnitude is mg, where m is the mass of the bar. Now what about the line of action of this weight? Well, it's very easy to see actually that it must be at the center of the bar. That's provided that the bar is uniform, of course. So we place it at the center. Well, if we want to prove why it's at the center, you know, we've divided our bar up into particles of mass dm. So these are presumably the smallest particles that we can divide it up into. Each particle is essentially a point. We get the moment of each of these forces about the center. The center is a convenient point here for taking moments about, but we don't have to take it about the center. We could take moments about any point. Well, these forces will have clockwise moments, or sorry, anti-clockwise moments about the point C. So the moments of these forces will be negative. But over here we have the exact same vectors. Okay, they have magnitude dmg because we're dividing it up, the bar up into equal masses. Each mass is dm. Okay, we just make all the masses equal for simplicity. It's a uniform bar, so we have just as many of them on this side as we have on the other side, but the moment of these weight vectors or gravitational forces about the point C will be positive. Okay, they'll have a clockwise turning effect. Actually, the usual convention is the other way around. You know, anti-clockwise is positive, clockwise is negative, but it won't actually matter. Because when we get the sum of the moments of all the weight vectors acting on the entire bar, we will get 0. Alright, so by the principle of moments, the sum of the moments about C is equal to the moment of the sum or resultant force about the point C. So if we want the moment of the resultant force about the point C to be 0, we must position the line of action of the resultant force at the center of the bar.